Yeah. Kita screen
now I baru klik. Okay, join green room. Tapi I belum masuk green room lagi.
You click join ya.
Ada join dah. Ya.
So share screen share screen.
Ya, dah.
Okay. So dia cannot see you lah ni.
Cannot see me.
Okay ni. It's okay ni. I replace you ni. I replace you.
Replace me, okay.
Okay. You send me the schedule ni.
Okay.
Okay. Good afternoon back to all. Right. First of all, thank you for joining Icias 2020. We will start with first presenter. Okay. Yeah. Okay. Before we start, as an audience, you can ask questions through the buttons live Q&A. So I will convey the questions on behalf to the presenter. Right. Without further ado, I would like to call our first presenter, Mr. Mavia Baba.
Assalamualaikum. My name is Mavia Baba and affiliated with University of Technology Petronas, Malaysia. Today I am presenting my paper in ESCON 2020 about International Conference on Intelligent and Advanced System. The title of the paper is about hybrid algorithm for optimal geometric display. My presentation outlines based on these content Introduction, literature review, scope of research, methodology, results and discussion, conclusion and references. Firstly, I will go through about the introduction section in which I will explain what is actually a phasor measurement unit and its OPV problem. Phasor measurement unit is a modern metering device used to estimate the voltage and current phasor in an electricity grid. This device, made by A.J. Fatke in 1980s, it replaces the old traditional system SCADA and converting it into a smart metering device system. It provides synchronized measurement with the help of global positioning system. It This device is installed at bus bars in a grid station. Here we have the novel device that is made by A.J. Patke University of Virginia. Figure 1 shows the novelty in the University of Virginia. It cannot be installed at every bus bar in a grid station due to the expensive nature of the device. Therefore, it needs optimal placement in the network. We have figure 2, which explains the installed number of PMUs in a grid station. Here we have 4 number of buses and 2 number of PMUs that installed at bus bar 1 and bus bar 4, which directly measures the parameter of voltage 1, which is bus bar 1, and V4 bus bar 4. The rest of the remaining parameter will be estimated through the KCL, KVL, node equation and Ohm's law. Recent survey on the PMU cost. The average overall cost per PMU, cost for procurement, installation and commissioning, ranges from 40,000 US dollar to 180,000 US dollar. As we can see, the cost is very much expensive and cannot be affordable to install at every bus bar in a grid station. Therefore, optimal placement of PMU is much needed in electrical system. Figure 3 shows the importance of PMU and allocation of PMU in North America. In 2009, we can see a less number of PMU were allocated in North America, whereas in 2014 we can see a abrupt change, and we can observe the abrupt change and massive change has been noticed with blue symbol. The blue symbol is shows that the location of PMU in North America. So this actually shows the importance of PMU for a modern world. So as we can see, the price is very much expensive. That is why different kind of optimization techniques have been developed to optimize and minimize the number of PMU and allocate the PMU in such a way that it will cover the parameters of the whole network. So therefore, different kinds of techniques are developed, namely mathematical method, heuristic method, and math-heuristic method. Below are the subgroups of these techniques. Literature review continues on 3 techniques. Mathematical technique. It involves integer value and uses complex mathematical data to solve the solution. It is time consuming and provides inaccurate outcomes. During problem solving, it first converts the problem into a mathematical shape. Equation and coordinate formulation are usually involved in it. The second method is an heuristic method. It comes into a consideration when traditional technique uh, uh, are too slow. It is often problem independent. Meta-heuristic technique, it is problem independent. It is a high-level procedure from heuristic that can be applied to a broad range of problems. It is used in real-time and natural-based problems. Scope of the research. The research focuses on the proposing the hybrid technique based on the previous method by taking IEEE standard test cases. Proposed approach is based on the new meta-heuristic technique. The IEEE datasets are available on a MatPower software, which is an open source tool for electrical power system simulation and optimizations. A hybrid approach for the OPV problem is considered in the proposed technique with the help of IEEE case system. The datasets are implemented on a MATLAB-based software for finding the existing gap in the current literature. Also, the IEEE single-line diagrams are obtained from the datasets which are used for the OPV problem, case factors, and validations of the proposed design. Methodology is initialized methodology begin with the exploration of the IEEE networks by the knowledge of all the bus's characteristics based on the bus data, branch data, etc. Searching a node, which is important for the optimum placement. The node which is load buses, generator buses, and in that buses we have focused on the bus which have more number of branches. So the preference will be given to those buses which have more number of branches, specifically load buses and generator buses, and then we'll move back, come down towards the removing the unimportant nodes. Those does not exist these kind of characteristics. So excluding these nodes, which improves the computational efficiency and improving the searching space of the network. And then the placing a PMU according to the above criteria mentioned about the load buses and generator buses. And then moved on towards the analysis of the system with the topological observability rules. These rules using the KCL and KVL law by placing the PMU in a network. As we have mentioned in the second slide of introduction that the placement of PMU should be in such a way that it will cover the whole network by using the KCL and KVL node equation. The example has been given in the second slide of the introduction. And then the last checkpoint is the system observability. Uh, if the system is not observable, then it will move back towards the searching a node. Again, it searches a node that comprises of load buses and generator buses with the maximum number of branches. And if our system is observable according to our criteria, then we'll end our algorithm. The system will end its performance. Proposed hybrid technique. This technique is based on the previous algorithms, namely graph theoretical procedure and recursive algorithm. We have combined these two algorithms. The parameters of these two algorithms are specifically combined with each other, and the performance has been improved with one another. The performance is improved of the current techniques by hybrid approach, and which enhances the searching space. Also, it selects the buses with the maximum branches, especially generator buses and load buses. The last section is about the results and discussion. The proposed work is tested using the material of IEEE bus networks which are taken from the MatPower toolbox. All the results of the proposed approach are displayed in the tabulated form. This is a result section, result table obtained by the proposed approach methodology for the OPE problem. We have 4 columns. The first column shows the IEEE bus network, starts from 9 buses, ends at IEEE 39. The other 3 columns shows the number of PMUs, bus location, algorithm time. For IEEE 9 bus network, we have 2 PMUs. The location of PMUs are 2 and 4. The algorithm time taken to allocate this PMU is 0.08. And respectively, the other buses have also optimal and better result, and we can see in the table 1. The second table shows the comparison result of the hybridized technique with the existing algorithm. We have again 4 columns. The first column shows the IEEE bus networks ranged from IEEE 9 to IEEE 39. And the proposed work results are compared with the graph technique and recursive algorithm. The number of PMUs we can see are very much less even in the small network. And in graph technique and recursive algorithm, we can see even for a smaller network, we can see a large number of PMUs are taken in their optimal placement results. So this shows the inaccuracy in their performance. That is why both the techniques have been combined together and make another hybrid algorithm to improve their efficiency and performance. So the proposed work results, we can see here the number of PMUs are decreased as well and improve the performance of the algorithm. So this table shows the importance of the proposed work with the comparison of the other technique. The final is about the conclusion. Deep theoretical investigation on the existing technique using IEEE case studies on OPP problem. A detailed study has been carried out on the existing technique's performance using the importance of IEEE case studies and its role in solving the OPP. Proposed hybrid technique. A hybrid technique has been proposed which enhances the overall performance of the algorithm when combining the GTH and RA parameters. Enhances the computational loading,
Yeah.
provides minimum number of VMUs as
Where
compared
to
to the
check whether
previous
got
method
question or
as
not?
we have observed in the previous slide.
Huh?
The validation of the proposed work. The validation of the proposed method is implemented and estimated on a MATLAB-based software. Moreover, in addition to show the effectiveness of the proposed method,
Live
the
Q&A.
outputs
Kalau
of the
tak ada,
proposed work are compared with the current studies.
huh?
These are the references used for the core paper. Finally, thank you for being with me.
And well, I don't see any questions from the audience. So can we proceed with the next presenter? Our next presenter is Christopher Jun Quinte. He is from University of Technology Petronas. And Christopher will be presenting on one diode PV modeling under varying radiance. Yeah, please proceed.
Welcome everyone that came to my presentation today. My name is Christopher. Today I will present to you my topic about one diode PV modeling under varying irradiance. So today the outline for today is first we will go through the introduction, then literature review, then is our methodology that includes the analytical parameter extraction and characteristic point translation. After that, then we will discuss the results, and finally is the conclusion. So in the 21st century, there are different types of technology have been developed to make our life easier. Nevertheless, one of the technology is called Internet of Things. So Internet of Things refers to billions of physical devices that have the ability to transfer the data over a network. And many industries have started to integrate IoT into their devices to collect meaningful data and increase their business competitiveness. So it can be applied on different types of applications such as health, military, industries, and many more. And WSN is a technology used within an IoT system, which can be shown in this figure. So WSN is also a type of flexible network that can adapt to changes such as adding a new node into the network. So in WSN, sensor nodes are normally the nodes who collect the informations and transmit the information to the sync node. Then the IoT will upload the information collected from the sync node to the cloud. However, some of these WSNs are still battery powered. So this is because finding a power supplies for WSNs at every desired location is very difficult. Therefore, this causes them to have a limited lifespan. So energy harvesting wireless sensor network are gaining attention these days because it is a promising solution where the ambient energy can be harvested and stored for the sensor node. Hence, this light energy harvesting systems, which uses the PV module, is chosen to be modeled in this research. So, based on my literature review, many works have chosen this one diode model, which is shown in this figure, because this model is simpler compared to the other models, while it is able to provide a high accuracy. So this model has a 5 parameter which is shown in this table, and these parameters are not provided by the manufacturer datasheet. So the parameters are needed to be obtained through a certain methods, so they can be used on this one diode equation to construct the IV curve. So as you can see in the IV curve, there will be 3 significant points: the short circuit point, maximum point, and the open circuit point. So to extract the parameters, there are 2 ways. So first one is the optimization. So with this optimization method, they will be using a different algorithms to iterate the parameters within a certain range in order to find the best fitted parameters. But the limitation of this method is that it requires experiment data. So without experiment data, the algorithm cannot be iterated or perform optimizations, and this will cause a problem to the researchers who do not have a proper equipment to collect data from the experiment. And not only that, the optimization method also requires a lot of these iterations, and this will also cause the low convergence rate. So on the other hand, analytical method is shown to be the better way, because this method is able to describe the behavior of each parameter using only analytical equations which derive from the one diode equations. So this method, not only that, this method also does not require the experiment data and uses only datasheet values. Analytical will be chosen in this research. PV will be also used at different operating conditions. Therefore, we need to have a method to predict the PV behavior at different operating conditions. So there will be 2 methods to do this. First one is the parameter scaling, and the job is to scale the 5 parameters of the one diode model to other operating conditions. However, this method shows that the accuracy of the parameter scaling will decrease at low irradiance level. So the next one is characteristic point translations, and this will translate the 3 characteristic points from the IV curve, again, which is the short circuit point, maximum point, and the open circuit points to the other conditions. So this method, it will give better results than the parameter scaling, and also a simpler way. So in the literature, most of the works, they perform the parameter extraction first, then they will do the predictions later. So as a result, this way will cause the accuracy to degrade at low irradiance level. Hence, our proposed model is to perform translation technique first, and then we will do the parameter extraction later. So by doing this, the accuracy can be improved, where the series resistance will be optimized in order to find the best accuracy. So normally, from a datasheet, the value given are based on standard test condition, STC. So this is an example that you can see. The table here is taken from a datasheet. So we have the 3 characteristic points value, and all of these are evaluated as STC. So STC refers to this 1000 watt per meter square, cell temperature at 25 degrees, and air mass 1.5. So not only that, you get these values at STC, and some data sheets will also give this IV curve. Okay, so we will have this IV curve on the horizontal line, and this one is the curve is the PV. So although these IV curves is given, but the values at this 800, 600, 400, and 200, the value are not given. So if we perform the optimizations, method, then the researcher will not be able to perform the algorithm. This is the characteristic points technique that will be used to translate the three characteristic points. Current will be changes proportionally to the irradiance level, and the voltage will be changes according to the coefficient C1 and C2. So after translate the 3 points, then those points will be used to extract the 5 parameters of the one diode model. So all of these equations are derived through the one diode equations. And number equation 3, where the diode ideality factor that will be used, there will be iterate from 1 to 2 in order to find the best accuracy. So for the results, commercial available panel model, this RSM72630 will be used. And this is a monocrystalline technology module. So this is the datasheet values that can be taken from manufacturer. So we have IMP, VMP, VOC, INC. This is the 3 characteristic points and the temperature coefficients value. So one translation work, which is the Wahid one, will be used as a reference to show the accuracy improved by the proposed model. So the datasheet value at STC are given already, and then the 800, 600, 400 are taken through the IV curve using the MATLAB graph. So it can be seen that at high irradiance level, both work can achieve a high accuracy, but as the irradiance level decreases, the percentage difference increasing slowly until at 200, where you can see Wahid has already have 7.225%. So while the accuracy of our proposed model that can maintain within 5% at all irradiance level. So for you to have a better visualization, so the values are plotted in the MATLAB. So you can see that the green one is the data sheet simply provided by the manufacturer. And then the circle one is the Wahid one, and the rectangle, triangle one is the proposed model. So this is at the high irradiance level. Both of the work can achieve high accuracies. And then when it turns into the low irradiance level, the accuracies can be, the accuracy degrades. So for conclusions, the proposed model can predict the IV curve accurately at different irradiance level. And the proposed model is using the one diode model that combines the translation first and parameter extraction technique. Also, the model requires only the datasheet value as input and does not experiment data to optimize the parameters. So finally, the proposed model is able to provide high accuracies at all irradiance level, and the accuracy of the model is better than the comparable. So that's all for my presentation today. Thank you very much.
Thank you very much, Mr. Christopher, for the presentation. Any questions? I don't see any questions from the audience. Okay, with that, we move on to the next presenter. The next presenter is Faisal Masood. Faisal Masood is from University Technology Petronas. And Faisal Masood will be presenting on design optimization and parametric analysis of compound parabolic concentrator for solar photovoltaic applications. Faisal, please proceed.
Assalamu alaikum and good day to all. My name is Faisal Masood and I am from University Technology Petronas, Malaysia. And the title of my presentation is Design and Parametric Analysis of Compound Parabolic Concentrator for Photovoltaic Application. Now let's start the presentation. First of all, Let's see what was the research motivation and what was the research problem. Solar PV panels suffer from the problems of low conversion efficiencies and higher costs. So one of the methods for enhancing the efficiency is by integrating optical concentrators with the solar PV panels. And these optical concentrators, they focus sunlight over the cell surface area. And these optical concentrators are relatively cheap as compared to the costly solar cells. And thus they cause a decrease in price. We can say that same PV output can be generated by lesser solar PV material by using optical concentrators. Figure 1 shows the basic concept of concentrating PV, whereas figure 2 shows a PV panel with one side glass reflector, whereas figure 3 shows a PV panel with reflectors on both sides. Although there are there are a number of different concentrators available for low concentration photovoltaic systems like booster reflectors, luminescent concentrators, holographic and V-type concentrators. However, compound parabolic concentrator, abbreviated as CPC, is considered to be one of the best low concentration photovoltaic concentrator due to its higher optical efficiency, wider acceptance angle, and being capable of collecting both direct and diffuse solar radiations. Now let's talk about the geometry of CPC. CPC belongs to a family of concentrators which we call non-imaging type concentrator. Since it is called a compound parabolic concentrator, it consists of two parabolic sections, two parabolas, parabola A and parabola B, as shown in figure 5, the schematic diagram of standard 2D CPC. And the focus of parabola A lies on parabola B and vice versa. And the portion of each parabola beyond the focus point of its counterpart is removed, which is shown as dashed line in the figure. Moreover, the axes of the two parabolic surfaces are displaced from the central CPC axis by an angle which we call acceptance half angle, and this acceptance half angle defines the angular range over which all rays incident on the entering aperture are accepted without a need of moving all or part of the concentrator. An important parameter to be discussed with concentrating collectors is their concentration ratio. For example, geometric concentration ratio or optical concentration ratio. Geometrical concentration ratio is defined as ratio of entry aperture width to exit aperture width, and it indicates the factor through which solar radiation is concentrated or intensified over the receiver. And this receiver may be a PV receiver or it may be a solar thermal collector, but here we are talking about particularly about PV receivers. An optical concentration ratio of an ideal CPC, that is a CPC having parabolas with no error, can be defined as the reciprocal of sine of angle theta c, where theta c is same half acceptance angle. Design concentrations. When we want to design a 2D CPC, initially we need two parameters. First is width of receiver and second one is acceptance half angle. We have to make a choice of these two parameters. Then the coordinates of one parabolic branch are first determined such that y-axis is identical with the central CPC axis and the origin lies on the focus point. And other branch is just the mirror image of first branch. Here in this research, first of all, we developed the equations, just analytical equations describing the geometry of CPC, and then a MATLAB code was written to generate the coordinates of both right and left reflectors of CPC, and then we plotted the profile. So if here is the CPC profile, this is figure 6 shows MATLAB generated profile of CPC, whereas figure 7 shows the table of design parameters of CPC. Acceptance half angle was chosen to be 20 degree, and the resulting concentration ratio was found to be 2.92x. Width of absorber was chosen to be 78 millimeter. The resulting width of entry aperture was found to be 228 millimeter. Height of CPC was found to be 410 millimeter, and apex point minus 34.5 and 100. Truncation, height of CPC and corresponding mirror area, they increase with increasing concentration ratio, and the effect is increased material consumption and manufacturing expenditures. So the upper portions of CPC, which are parallel to the optical or the central axis, they contribute very little to the size of the entrance aperture, and hence the geometric concentration ratio is minutely affected if we cut off or truncate these upper portions. So here we truncated above 50% height, and figure 8 shows the truncated concentrator. Here are the results. First of all, figure 9 shows the CPC height, aperture width, and its concentration ratio versus acceptance of angle. For this purpose, we changed the acceptance of angle from its initial value of 10 degree to final value of 90 degree. Concentration ratio decreases with increasing acceptance of angle, and so does the CPC height and width of the entry aperture. For lower half acceptance angle, for example 10 degree, concentration ratio is maximum, but the height attains a very large value, and so does the width of entry aperture. So actually we have to choose a value of acceptance of angle for which we can obtain a suitable concentration ratio and lesser height. Concentration ratio, when it is maximum, CPC height is too much. And the next figure 10, it shows the height and aperture width versus absorber width for acceptance of angle of 20 degree. For this purpose, the value of absorber width was varied from its initial value of 78 millimeter to 780 millimeter to accommodate larger solar cells or PV modules. And the effect on height and aperture width, that is shown here, as the absorber width increases, both CPC height and aperture width also increase, and here is the concentration ratio and height versus truncation level. As the truncation level increases, CPC height decreases, so total mirror area also decreases, and CPC cost and space required for its installation decreases. Here are the conclusions. In this research, we designed a 2D symmetric CPC by solving the analytical equations using a MATLAB program. Then we performed a parametric analysis, and we observed the variation in CPC height, width of entry aperture, and with the variation of acceptance of angle.
Okay, thank you very much, Mr. for that wonderful presentation. Now the floor is open to questions from the audience. Any questions? Okay, thank you very much, Mr. Faisal.
Thanks.
We move on to the next speaker. Our next speaker is Mr. Raymond Wong. Raymond Wong is from University Technology Petronas. Now, Raymond Wong will be presenting a paper on an enhanced voltage gain switch Z source converter with minimal components contact. Mr. Raymond, please proceed.
Hello, welcome. My name is Raymond Wong, and today I'm going to present this paper entitled Fault Classification and Location in Three-Phase Transmission Line using Wavelet-Based Machine Learning. So this was done by one of my final year project students. So without further ado, let me introduce the presentation outline for today. I will start with a simple introduction on the type of faults in the transmission line, followed by the objectives of this work. Next, I will describe the methodology, which is on the PSCAD simulation, the parameters, the feature extractions, and also the fault classification and location. Then I will continue with the result and discussion before ending with a conclusion for this presentation. Right. So here's a brief introduction. The transmission line that we have currently are susceptible to faults because since it is exposed to the environment factors, so eventually faults will occur every now and then. So a few examples of the type of faults are single phase to ground faults, represented by L-3, line to ground, or two-phase faults, line to line faults, two-phase to ground faults, three-phase faults, and also three-phase to ground faults. Okay. So if the fault remains unnoticed in the transmission line, it will cause electrical power disruption, equipment damage, and human fatality as well. So it is best we can detect it as soon as possible. So transmission lines are very long, so it can reach up to few hundred kilometers or more. So the locating of the fault manually is very challenging as well as time consuming because the fault could occur anywhere in between the segments. Right? So the voltage and the current waveform shortly before the fault, it has some information. So this information may be difficult for human to detect, but with a well-trained machine learning model, you can get some insights on the nature of the fault. Okay, so by using proper feature extraction, the type of fault and also the fault location can be roughly estimated using machine learning techniques, which is much better than manually trying to search the fault location. Okay. So if the fault type and also the fault location can be estimated, so this will greatly speed up the reparation process and also minimize the downtime. So the objective of this work is to try to simulate and collect data, fault data using PSCAD. We have to do simulation because it's not possible to have an actual power system available for us to experiment with. Next is to perform feature extraction. Feature extraction is the process of obtaining information from raw data so that you can use to train your machine learning models. So the feature extraction we'll be using is a discrete wavelet transform. Okay, so once we have the data, the information from the feature extraction, it will be used to train machine learning models so that they can classify the fault type. What type of fault is it? Is it a line to ground or line to line fault, etc.? As well as estimate the fault location, which segment did the fault occur. Okay. And lastly is to compare the performance of different mother wavelet and also the performance of different machine learning models. So this is the simple model of the simulation. The simulated line is around 300 kilometers. It has 19 segments, which are 15 kilometers apart for each segment. So the fault types that we simulated, we have single line to ground faults, two-phase faults, two-phase to ground fault, and three-phase to ground faults. So there are total a number of 7 types of fault. Okay, and the fault inception angle, we try to simulate it at many different angles from 0 to 360 degrees at 45 degrees intervals. And the fault impedance, we vary it from 0 ohms all the way up to 250 ohms. For the fault location, we can't really pinpoint the exact location, but we can narrow it down to at least around 15 kilometers intervals. Okay, so these are the intervals where we try to detect the faults. So overall, this is the summary of the fault data that we've collected. There are 81 different samples just by adjusting the inception angle and also the impedance value. And since there are 16 fault locations, so 16 multiplied 81, we have 1296 samples for each fault signal. And since there are 10 types, so we multiply 10 again to this value. So a total of around 12,000 data samples were collected. So among this data, 60% will be used for testing, 20% for validation, and balance remaining 20% will be used for testing. So for the mother wavelet selection in the feature extraction, we have tested 12 different mother wavelet. And this one we did a lot of try and error by comparing the accuracy of all the other classifiers. Overall, it seems that the HA mother wavelet has achieved the best accuracy for fault classification as well as fault location. So that was chosen to be the benchmark. So the upcoming slides, the comparison will be using HA wavelet. So this is the fault classification accuracy performance by using different machine learning models. So we have tested k-nearest neighbor, decision trees, random forest, neural network, Bayes, naive Bayes, and also ADA boost. So from here, the neural network has the best classification accuracy. And for the fault location, just now one is a fault type classification. Now for the fault location estimate, so this one, the performance is lesser because it is naturally more difficult to estimate the location of the fault rather than determining the type of fault. Because type of fault is only a very few number of types, but the fault location, there are many segments. So naturally, it is more challenging. As can be seen here, all the performance of every machine learning model is slightly lower compared to the fault classification, right? So even so, the best performance here is again the neural network where it achieved a 95.9% accuracy. So the fault estimation value, overall error percentage for each zone. So you can see here for as the faults proceed further, so the overall error tends to reduce, and the highest percentage error is from the range between 60 and also 90 kilometers. So overall, fault location is definitely more challenging compared to fault classification because of the nature of the task being assigned. Okay, so in this case, we have tried multiple machine learning models, and artificial neural network (ANN) it has the best performance for fault location and also fault classification compared to other machine learning models. And most of the fault estimation error that occurs are between 3 to 6 kilometers. So if we try to test this, the worst case scenario, let's say both it is between 6 kilometers, so plus minus 6 kilometers. So the fault could be narrowed down to a zone of 12 km. So this is definitely better compared to the 15 km segment. Okay, so by using this algorithm, it does help to speed up the reparation process by narrowing down the location of the fault. Okay, so in conclusion, fault classification is not so challenging as a fault location. So by using neural network, we can achieve up to 100% accuracy. For fault location, we can get up to 95.9%. And overall, this method is considered quite cost efficient because it just uses a means of data. It just monitor data from the CT or VT. So it is relatively simple and low cost. We just need more data rather than new measurement. Okay. So thank you very much for listening. That's all from my presentation.
Thank you very much, Raymond, for that wonderful presentation on fault classification and location in three-phase transmission lines using wavelet-based machine learning. And Raymond is from Tunku Abdul Rahman College. Friends, I open the session for any questions from the floor. Okay, there's one question, Raymond, for you. This method, is it suitable for large system as well, or has it got its own limitations?
Theoretically, hi, can you hear me?
Can I repeat the question? The question is this system suitable for large-scale systems?
Large scale. At the moment, additional testing needs to be done because to be used for a large-scale system, we need more. We need some data from real-time simulation. So right now, this was not done in real time, but theoretically, it can be used.
So your system is limited to what? A simple three-phase system?
Yes.
Right. Okay, thank you very much, Raymond. Okay, so we move on to the next presenter. The next presenter is Rahul Kumar. And Rahul Kumar will present a paper on an enhanced voltage gain switch Z source converter with minimal computer contact. Rahul, please proceed.
Hello everyone, I am Rahul Kumar. I am doing my Masters in the Department of Electrical Electronics Engineering. First of all, I would like to thank you, ESCOM, for providing me a chance to present my research in this conference. The topic for my presentation is performance analysis of high-gain jet source DC-DC boost converter. These are the contents of today's presentation. Starting with a brief introduction, as we know that the electrical energy is a fundamental need of every nation, because for running a small fan or big machinery we need the electrical energy. There are different ways by which we can generate the electrical energy, such as coal-based plants, gas plants. However, the current trend is to generate the electricity from the renewable energy sources. Now, the reason behind that is that renewable energy sources are natural sources, so they are widely available and cheaper. Apart from this, they have some disadvantages as well. As I mentioned, that they are natural sources, so they totally depend upon the nature. For suppose if we are talking about the PV sources, the output of the PV panel will be decided by the intensity of the sun. To avoid this, we have alternative that is known as PCS, power conditioning system. Basically, power conditioning system is consist of renewable energy source, power converter, and the load. So to improve the performance of the power PCS, the design of the power converters is very important. So basically this research is totally focusing on the designing of the DC to DC converter to improve the performance of the PCS. There are different DC to DC converters available in the literature. The one I am focusing is the Z source converter. Basically, Z source converter is similar to the traditional DC-DC converter. The difference is that we have replaced the inductor with a Z network. Now it has advantage that it can buck and boost, means it can be used as a buck converter and as well as a boost converter. The other advantages are higher boost factor compared to conventional converters. Some disadvantages are higher capacitor voltage stress, high startup current, and utilization of high duty cycle for higher gain. Now, to avoid this type of disadvantages, there are different techniques and topologies available in the literature. For suppose if we are talking about the voltage multiplier cells, so basically the voltage multiplier cell is one of the technique by which we can enhance the gain of the Z source converter. There are some cells which we employ to the Z source converter, so that then output of the converter can be higher. Now what we are doing basically, if we want to get the higher gain, we are increasing the external number of the components. If I sum up my research paper, research statement on which I am working is, it will be like we should not use the higher number of the components to get the higher voltage gain. Why? Because at the one side we are getting the advantages of higher gain, but on the other side we are increasing the size, cost and weight of the converter. So in a nutshell, the objective of this research will be to minimize the number of the components, or to reduce as low as possible the number of the components and obtain the higher voltage gain while maintaining the reduced number of the components. So these are the first objective. The other objectives are the performance analysis of opposite source converter, the one which will be proposed. The performance will be analyzed for that, and also the comparative analysis. The performance will be compared with the traditional converters in different perspective, like number of the components or the gain. So this is the proposed design. Basically, if we focus on the circuit diagram, it is similar to the traditional Z source converter. However, there is small difference, that is the capacitor C3 is connected in a different way here. Normally this capacitor is a filter capacitor which we use for the filtering purpose, but here it is helping in charging and discharging loops of the inductor. It's also helping in increasing the gain of the converter. So that's how the obtained gain from the proposed converter is higher compared to the other converters. Other features or advantages for the proposed converter are the number of the components is reduced. We will obtain the higher gain with the low duty cycle that I will prove in the simulation section, result section, and the starting current is also reduced with this topology. So these are the operating principle. There are two operating principle or two states for the proposed converter. One is when switches are on and then is when switches are off. Diode Diodes always act as a complementary, means when switch will be on, the diode will be off, and vice versa. So in the state one, when the switches are on, the capacitors are to be charged and they will discharge the energy to the inductors. Inductors will store the energy, and in the second state, the stored energy in the inductors will be discharged to the capacitors, and capacitor will be charged, and load will be supplied by the C3. So this is how it works. This section is basically the performance analysis with the parasitic parameters. Basically, the parasitic parameters are the internal resistances. We know that every component has some resistance in real, for example, even it's the inductor or switch. So how these resistances affect the performance of the converter, this will be justified here in this section. So for the analysis purpose, these parameters have been taken, which are shown in table 1. And the output or the graph has been drawn with the different parameters of parasitic parameters. But what we can see from the graph is when we are increasing the values of R and VD, R is basically the resistance, the internal resistance on the inductor, and VD is the voltage drop across the diode, the output voltages keep on decreasing. So what we can conclude is that as higher the parasitic parameters you have, as lower will be your output voltage. So while designing the real parameters or real experimental results, we must consider these things in our mind, that definitely we will have some effect on our converter because of these parasitic parameters. So these are the simulation results. Basically, three different converters are compared. One is the proposed converter, obviously, and two others are conventional hybrid. Hybrid Z source is one of the predominant topologies in the literature. So similar conditions we have used for all three to justify the superiority of the proposed converter. We can see that in figure 7, the duty cycle is used 0.15, which is for all three converters, and also the input voltage is 30 volt. So which is also used for all three converters. The output voltage we get is 130 for proposed, hybrid converter 70 volt, and the conventional converter 36 volt respectively. So from this we can clearly see that the proposed design obtains the higher output voltage. So if the output voltage is higher, definitely the gain will be higher, because the gain is always calculated by the dividing the output over input. So also the comparison between the starting current is here. The proposed converter has 26 ampere. The other converters, like conventional, has 3300 ampere, and hybrid converter has a 180 ampere. So also the proposed converter has reduced startup current compared to the other converters. Moreover, this result is for the capacitor voltages, which can be justified through the equations provided in the research paper. That also at the similar conditions, the capacitor voltage can be calculated as 86 voltage, which is near to these results. So to conclude, in this work, basically we designed the Z-source DC-DC converter. The drive gain 3 minus 4 divided by 1 minus 3 specify that the boost ability of the Z-source converter has significantly improved. The performance is analyzed with the parasitic parameters. The simulation results are obtained and compared with the traditional converters such as hybrid Z-source and conventional, and the results clearly demonstrate the superiority of the proposed converter over conventional converter. Thank you so much.
Okay, thank you very much, Mr. Rahul,
Thank you.
on your presentation of this interesting paper on an enhanced voltage gain switch Z source converter with minimal components contact.
Thank you.
Ladies and gentlemen, now it's open to the floor for any questions. Okay. All right. I think there's no questions from the floor. Thank you very much again.
Thank you. Thank you, Professor.
Rahul.
Thank you, Professor.
Our next presenter is Mr. S.M. Sanzid Luman. He's from University Technology Petronas. And Samzad will present a paper on prospect of regenerative current breaking in DC breaker topology. Sanzad is from University Technology Petronas. Mr. S.M. Sanzad, please proceed.
Assalamualaikum. Welcome everyone to my paper presentation at the ESTCon 2020 conference. This is S.M. Sanjay Lumen doing Masters by Research at the University of Technology Petronas. The title of the paper I am going to present today is Prospects of Regenerative Current Breaking in DC Circuit Breaker Topology. The contents of these presentations are as follows: introduction, background, literature review, problem statement, followed by the proposed work, simulation result, and conclusion. Let's take a look at the introduction of this research. We know that DC power system has attracted significant attention over the last few decades in both academia and industry. Because of it has lots of advantages and superiority over the AC power system in terms of reliability, efficiency, control simplicity, integration of renewable energy, and others. But still, despite having these numerous advantages, designing and implementing an appropriate production system for DC power system remains a significant challenge, and the main challenge is to interrupt DC current which does not have any natural zero crossing point like AC current has. In addition to that, DC network has some considerable amount of inductances, and under normal operating condition, these inductances store energy as half Li square, and this energy always opposes the instantaneous current breaking. So this energy needs to be dissipated during the current breaking process. In order to break current in any network, circuit breakers are used, and the circuit breakers usually make a break in the current path by isolating the contact mechanically or by solid state turn-off process. And DC circuit breaker is this critical technology to break DC current in any DC network, and its special circuitry forces the network current to become zero beforehand. Existing DCCB topologies use Naber network, nonlinear resistor, or a combination of them to dissipate the network, the stored energy of the network during every current breaking process as a heat. In AC network, due to the sinusoidal nature of the current, natural current zero situation arises twice in a full cycle. Using different arc extinguishing techniques such as arc cooling, arc lengthening, or increasing dielectric strength of the medium, current zero instances. If we look at the figure number 1, we can see this is the point where the current zero situation arises, natural current zero point. At this point, there is no current into the network, so there is no arc, and the arc as well as the current is extinguished quite easily. But this is not the case in the DC network. Though the process of current breaking in AC network is quite straightforward, but the breaking of current in DC network is quite challenging. It's because we can see from figure 3 the DC fault current nature. It has a peak value, peak current, followed by some steady state non-zero value. So using the traditional circuit breaker to break this non-zero DC current is quite challenging and quite impractical. So as per literature review, we have found that basically the DC circuit breakers are classified into these 4 categories: mechanical, solid state, hybrid, jet source circuit breaker, and there are some other modified versions of each of them are available in the literature as well. So this is the mechanical circuit breaker, the solid state circuit breaker, jet source circuit breaker, and the hybrid circuit breaker. The operation principle of these circuit breakers are out of the scope of this presentation, so I'm not going into details into them. So what are the drawback of this traditional circuit breakers? They have a common drawback in terms of current breaking technique, that all the topologies they use lossy element like the resistor or the metal oxide resistor or a combination of them to dissipate the stored energy of the network as heat during the every current breaking process. So if we can see in the mechanical circuit breaker, we can see the surge arrestor as well as this resistance. They also dissipate the network energy as heat during the current reduction process. The solid state circuit breaker, it got the surge arrestor, which is the lossy element of this circuit breaker topology. The jet source circuit breaker also got this resistance, and the hybrid circuit breaker as well got this lossy element. So all the modified versions of them also got quite similar kind of current breaking approach, which is that the network energy, the stored energy in the network inductance has to be dissipated by some means by this conventional circuit breaker topology. So the problem statement is this conventional current breaking technique makes the DCCB operation quite inefficient, especially if it is a highly inductive network, because a lot of energy could be wasted during every current breaking or switching operation. However, this instead of dissipating this energy could be reused like a similar way like the regenerative braking does in electrical drive system. But in the from the knowledge of literature, there is hardly found any study that deals with the energy reuse capability of a DCCB. So a new DCCB topology with energy reuse capability will make the DCCB operation much more efficient and will enhance the overall performance of the system. So in this research, we are going to, we have proposed a new circuit breaker, DC circuit breaker topology. This is the new proposed circuit breaker topology, which is made of these 2 few mechanical switch and couple of electronic devices. We can see from here that there are two mechanical switches, S1, S2, two thyristor T1 and T2, IGBT, and some passive element and diode as well. So how this circuit breaker works? Let's take a look at the working principle of this circuit breaker. This circuit breaker operation is basically divided into two categories or two steps: the current breaking operation and regeneration operation. So this is the let's take a look at how the circuit breaker is going to break the current. So under normal operating condition, both switch S1 and S2 both will be turned on. So the current will be flowing through this path to the load RL. Let's say, for example, the current is flowing as I naught. So once the circuit breaker receives a trip signal, what will happen? The switch S2 will turn off. Once the switch S2 turn off, so current and at the same time, firing pulse will be sent to this thyristor T1 and T2 that will turn them on. So the current will now have a alternative path, and the current will flow through this capacitor C and inductor L and goes to the load. So what will happen now? This impedance network with the combination of L and C, they will create some resonance network, and will create resonance oscillation. If we take a look at the mathematical modeling of this current breaking approach, the current response is governed by this equation. If we take the closed loop and use the Kirchhoff's voltage law, then we can get this equation, the characteristics equation, and the solution of this equation could be, if there is no resistance in this network, it could be pure sinusoidal oscillation. But as we can see, there is some resistance here, the source resistance as well as the load resistance. So instead of this pure sinusoidal oscillation, it will be a damped oscillation. And from this damped oscillation, we can see the natural current zero points are created. So that was the ultimate goal of current breaking approach for a DC circuit breaker, that we need a current 0 point. So you can see from here the number 3, damped oscillation. This is the current 0 point. So at this current 0 point, what will happen? Both resistor T1 and T2 will turn off, and that will ensure the successful current breaking operation. At the same time, what will happen? The capacitor will remain charged. All the energy stored in the earlier stored in the network inductance will be transferred to this capacitance. Now the current regeneration operation will take place. So what will happen now? The IGBT will turn on, so the capacitor will now discharge through this inductor. So all the energy of this capacitor will be transferred to this inductor. And once the capacitor energy becomes 0, then the IGBT will turn off. So now the inductor will force the current to flow back to the source. That is called the regeneration. So let's take a look at the mathematical modeling of this regeneration. The regeneration is divided into two steps. Step 1, when the capacitor discharges through this inductor, the current response is governed by this equation, and the solution of this equation is pure sinusoidal oscillation. So when the current becomes peak and the capacitor voltage becomes 0, that means all the energy of the capacitor has been transferred to this inductor, so the IGBT will turn off. Next, in step 2, now the inductor will release this current through the inductor because it doesn't have any other alternative path. And now the current response is governed by this equation, and the solution of this equation will give us this exponential decayed current. So this is the regenerated current as defined in this research. This is the operation sequence. So whatever I have described earlier has been shown in this diagram. We use the PSIM software for simulation. This is a simple radial network where this proposed DCCP has been applied, and the current breaking as well as regeneration operation was tested. These are the simulation parameters. The simulation was run for 0.3 seconds, and the source voltage was 400 volt, and these are the other parameters as well. It was the load current or the fault current was considered the 400 ampere. So this circuit breaker is supposed to break this 400 ampere current. So once the circuit breaker turned on, we can see the source current rises, the load current also rises the same. And at this point, the circuit breaker receives a trip signal, so the current becomes 0. This is the current breaking moment. And at the same time, we can see during the current breaking, and there is a voltage surge across the switch S2 is because of the arcing and sudden changing of the current. And this is the current for the impedance network. Because the source current is diverted into the impedance network, this is the impedance network of the capacitor current. Again, we can see this is the impedance network current while the current flows to the capacitor after being bypassed. So the capacitor voltage rises and it remains at this level. Then the regeneration starts at this point. So capacitor voltage becomes 0. capacitor current become negative because it's discharging, and this is the inductor current is also negative, and this inductor current is fed back to the source in the regeneration cycle. So this is the complete operation cycle. We can see this is the forward current. The current has been broken at this point, then the regeneration starts, and this is the regenerated current. We can see from here that the regenerated current has a peak value of minus 380 ampere peak. The source voltage got some fluctuation during the regeneration though, and this is the source power, this is the forward power, and the negative power with a peak value of minus 268 kilowatt peak. So the simulation results is summarized as below. The current breaking time was measured as 2.77 millisecond. After receiving the trip signal, within 2.77 millisecond, the current was broken. The regenerated current has a peak value of minus 380 ampere peak and an average value of minus 1.44 ampere. The regenerated power is minus 268 kilo peak, and the regenerated energy was measured as 140 joule. So the conclusion of this paper is that it was found that from the simulation result that around 0.62 kilowatt of average power with a peak value of 268 kilowatt had been regenerated from the breaking 400 ampere current. The amount of energy that can be regenerated totally depends on the current that needs to be broken and the system inductance. In this simulation, the amount of regenerated energy was calculated as 140 joule. However, it was noticed that the regenerated power had a spiky wave shape, and that created some fluctuation in the system voltage. And this power surge is basically due to the very short duration of the regenerated power. Because the duration is very short, that's why it becomes impulsive in nature. And a large voltage spike was observed during the breaker turn-up process as well. So it needs to be studied further that how to make this wave shape of the regenerated current as well as the regenerated power smoother while being feedback into the system. It has to be smoother instead of the spiky wave shape, and how to keep the system voltage within the acceptable limit during the breaker turn-up process. These are the references that have been used in this paper. So that's all from my side. Thank you very much. If you have any queries related to this presentation or related to this paper, please feel free to contact at the below mentioned address. Thank you very much.
Thank you very much, Mr. Ted, for that interesting presentation on the prospect of regenerative current breaking in DC breaker topology. Friend, the audience now, is there any clarifications or questions from the audience? Okay, we have come to the end of the session. On behalf of the organizing committee and the UTP and this session, I would like to take this opportunity to thank all the presenters for your wonderful presentation and the audience for your patience in listening to these presentations and raising some relevant questions. Thank you very much. Take care. Bye. Yes.